So let's start with a simple system of linear equations, that is 2x plus y is equals to 3 and x minus 2y is equals to minus 1. This is a two variable linear system. So every one of us know how to solve this system, right? So, and the solution is you can actually do what? You can apply the elimination method or substitution method to solve the system. And if you do that, you are going to find that so 2x plus y is equals to 3. And if I multiply the second equation with 2, then it will be 2x minus 4y is equals to minus 2. And now if I add these two, then it will be like, sorry, if I subtract this 2, this is a minus and this is a plus, so this is also a plus. So I can cancel these two things, and this is add up to 5y is equals to 5. So the solution for y is equals to 1. Similarly, you can find out that the solution of x is also equals to 1. So the solution of this system, this is actually what? X equal to y equal to 1, right? So solution of this system x equals to y equals to 1. So let's see this system of linear equation from a different perspective. So what we can do is we can plot these two equation of lines in a 2D space, and to do that, what we are going to do, we are going to introduce the 2D plane. And if I plot these two equations, 2x plus y equal to 3 and x minus 2y is equals to minus 1, then what we are going to get is so 2x, that means if I set x equal to, so if I set x equal to 1, then I'm getting y is equals to, so right, so that means y equals to 1, and if I set x equal to 0, then it will be y equal to 3, and finally if I set x equal to 2, it will be 4, y equals to minus 1. Minus 1. And now, if I plot this, this will be like 1, 1, this, 0, 3, 0, sorry. So the line will be like, this is a point, so this is a point, and 2 minus 1, this is a point. So the line will be like, for the first equation, and for the second equation, if I follow the same rule, x, y, x equal to 0, this is going to be y equals to half, x equal to 1, y equals to 1, x equal to 3, y equal to minus 2. So 2. And if I again plot this, this is like 0 half 1 1 3 2. So as you can see, these two lines intersected at the point 1 comma 1, right? And we saw previously that the solution of this system is 1 comma 1. So this is a visualization of this linear system in a 2D plane. So another perspective can be like, I can write the coefficients of x. So the linear system is 2x plus y is equals to 3 and x minus 2y is equals to minus 1. So now the coefficients of x, what are these? So if I just extract the coefficients of x, this is like 2, 1. And if I set it in a list of numbers like 2, 1, these are the coefficients of x, right? And similarly, I can extract the coefficients of y, that is 1, minus 2, right? So the linear system I can write as the 2, 1 multiplied by x plus 1, 2 with y, sorry, that's a minus 2, y is equals to 3 minus 1, right? So now, can any one of you remind me the definition of vector from an elementary physics perspective? So we learned the definition of vector in a physics book in our school and college. It is what? This is an object with magnitude and direction, right? And is there any student from CS or CSE? Do you know what they mean when they say the term vector? Yeah. They say the vector is a list of numbers. Okay. So as you can see, so it is a column vector. What I defined like 2, 1, and 1 minus 2. But still, I didn't define the column vector and what a vector is. So let's just take it for now. And so let us see how these two definitions from a different perspective, I mean from the physics perspective and from the CS perspective, and why the mathematician want to use a different definition of vector and vector spaces. So it is the mathematicians are actually trying to generalize these definitions of vectors from different fields so that it is possible to explain everything in just one settings. Okay, so now let us say, so we already saw that the solution of this system is what? X equal to y equal to 1, right? And if we, so let us take that the CS definition of vector. This is 2, 1, the list of number. So, and if I plot this list of number 2, 1 as a coordinates of this two-dimensional space R2 plane. So this is what? This is just 1 and 2, then 1 and 2. this is the point, and the second one is 1 minus 2, right? So it is 1 so 1 and this is minus 2. So now if we use the definition of physics, the vector is like this, right? A arrow, and so this is also this, right? So now from the vector addition, we know that if I complete this parallelogram, so the diagonal of this parallelogram will be what? The resultant of these two vectors, right? So if I this is the resultant of this two vector, and now if I just use the solution x equal to 1 and y equal to 1, then what I'm getting is 2 1 plus 1 minus 2, this is equal to 3 and minus 1, right? So that means what we did in this in here is, sorry, in here is we take the linear combination, and let us just for now, let's define this as a vector v1 and the vector v2, and if I set the solution x equal to y equal to 1, then it is actually equal to the resultant, that is 3 minus 1, right? So you see, when you are considering the vector in mathematics, you are taking just the addition of two vectors and the multiplication with a coefficients like here x and y. So actually the mathematical definition of vector space and vector will be based on these two operations, the multiplication and the addition. Okay, so these are the motivation. So, and finally, the thing that I want to introduce you, if I just combine these two vectors v1 and v2 to a matrix like a rectangular array of numbers, then this will be 2 1 1 minus 2 minus 2, and if I take x y like this, then this is equal to 3 minus 1. Right? So this is defined as a matrix A, and it is a column vector x, and this is some coefficient b. So the matrix equation will be A x equals to b. So although I didn't define what a matrix is, just this is the motivation. So why we are considering the matrix and vectors in linear algebra. Okay. So let us define the vector, the matrix from rigorously. So a matrix is a rectangular array of numbers, symbol or expression. This is the definition of the matrix. So, but for our case, it is always be the numbers, and the numbers will come from a field that is I still didn't define. So, for our case, this is a matrix is a rectangular array of numbers, and it can be written as A is equals to A11, A12, A1n, A21, A22, A2n, AM, A M1, M2, Mn. So, what are these subscript of A's? These are the index of the elements. So, the numbers Aij called the entries of this matrix. So here it is very important that we have to define what is the size of this matrix, the dimension of this matrix. So I mean the size of this matrix is the number of rows times the number of columns. So here as you can see, the number of rows is actually what is m, and the number of column is n. So it is the size of this matrix is actually m cross n. So A is a m cross n matrix. And so I runs from 1 to m and j runs from 1 to n. Okay. Now the matrix A, okay, so let me introduce. So I is the row index and j is column index. Okay. So A, from this matrix we can see that depending on m and n, the matrix can have different size, right? So a simple form is like A 1 cross n is called a row vector and n dimensional row vector. And what is the representation of this? This is A equals to A11, A12, and this is A1. Similarly, we can define the column vector and a m cross 1, so there should be a matrix So a M cross 1 matrix is called an M dimensional column vector. Okay. So since we have defined what a matrix is, we need to define what are the operations or what we can do with these matrices. So matrices. So the first thing we are going to define is how to add two matrices. So to add two matrices, it is defined as the size of these two matrices has to be equal. Otherwise, it is not possible to define the addition. So A is a matrix of size, let's say M cross N, and B is a matrix of size M cross N, then we can define the addition between these two matrices. And how do you do that? We are just adding the elements of this matrix, these two matrices. So let's A. So if Aij plus Bij is equals to the resultant matrix, the summation is ij, where A is the Aij is an entry of A, and Bij is an entry of the matrix B, and the summation is defined this way. So Aij plus Bij is equals to Sij. We can see a simple example, and this is like 2, 1, 0, 1, 3, 5. If I add it with 1, 0, 3 with 4, minus 3, 1, what will be the result then? Okay, so we have to add the element of these two matrices, right? So this is 3, 1, 3, and 5, 0, and 6. So this is an example of matrix addition. And now let us define the how do you scale a matrix. I mean, how to multiply a number, scalar number with this matrix. And this is like so if C is a number, then C times a matrix A is equals to what this is. I have to multiply it with all the entries of the matrix, right? So this is in general C times Aij, where I and J are what? The row index and the column index of this matrix, right? So as you can see, we can add two matrices as well as we can multiply a number with the matrix. So now let us define the multiplication of two matrices. So do you think is it possible to multiply any arbitrary two matrices with each other? So the matrix multiplication is defined in a proper way, and to do that we have to consider two different matrices. Like, let's say A is a matrix of size m cross n and B is another matrix of size L cross P. So to define the matrix multiplication between these two matrices, we have to take this column of this first matrix and the row of this second matrix. These two has to be equal, otherwise it is not possible to define the matrix multiplication. So to make sense the multiplication of the matrix, it is we need to consider n is equals to L. Then the after the multiplication, what we are going to have is m cross n with b L cross p. This is equals to some matrix, let's say C, and the size of this matrix will be m cross p. Okay, the resultant matrix is like the row of the matrix is the matrix of the first matrix and the column is coming from the second matrix, right? So in general this can be defined as like AB is equals to the matrix Cij, and Cij is defined as, you can use the summation notation here, k equals to 1 to n, right? And this is A I k with B k j. So this is the matrix multiplication, and we can consider an example here. So let's consider A is equals to 0, minus 1, 2, 3, 4, minus 6, and B is equals to 1, 2, minus 1, 3, and 4, 2. Now, without even multiply these two matrices, we know what is the size of the resultant matrix, right? So the after the multiplication, it will be like, so first it is possible that these two matrices can be multiplied, right? So the number of columns in the first matrix is what? It is 3, and the number of rows in the second matrix is 3. So since these two numbers get matched, we can definitely multiply these two matrices. And so finally the AB multiplication is like, so can you tell me what is the size of the matrix that have been come after the multiplication? It is a 2 cross 2 matrix, and so AB will be 9, 1, minus 25 with 6. And so if I follow this formula Cij, I can write like C11 will be what? This is the matrix C. So C11 actually what? This is 9, right? So since it is 9, what we can write is, this is A11 plus B11 plus A12 B21 plus A13 B31, and this is equal to so if I multiply this 0 with 1s, that is 0, minus 1 with minus 1, that is 1, and 2 with 4, that is 8.
It should be A11 times.
Sorry.
First term.
Yeah. This is just A11 with B11. Where the A11 entries comes from the matrix A and B11 entries comes from the matrix B, right? So A and B, the lowercase letter A and B comes from the matrix A and matrix B, right? So this is the matrix multiplication, and this is equals to 9. Similarly, we can find out that C12 is equals to 0 minus 0 minus 3 plus 4 is equals to 1, and C13 will be, sorry, C21 will be 3 minus 4 minus 24 is equals to minus 25, and C22 is equals to 6 plus 12 minus 12, which is equals to 6. Okay. So now let us introduce you with some identities of matrix that I'm not going to prove, but it is easy to prove, and you can find the proof in any standard book of linear algebra. The first one is the distributive law. So the distributive law is defined like A times the matrix B plus B prime. This is equals to AB plus AB prime. Here, one thing that needs to be clear, that I didn't mention is it possible to multiply A and B, so I'm taking that the multiplication is possible between A and B and A and B prime. So the size actually satisfies the matrix multiplication. And the second is the associative law. And associative law is like A, B times C is equals to A times B, C. So what the associative law is telling us that if I multiply two matrix A, B, and then I multiply it with another matrix C, this will be equal to, if I multiply first the matrix B and C, then multiply with A, these two result will be the same. Okay, this is the associative law. And so scalar multiplication is also makes sense this way, and this is like multiplication. So if C is a number, is a scalar, and A and B are two matrices, then this is equals to C times A with B is equals to A times C B. Okay. Finally, the commutative law of matrix multiplication is not actually, the matrix multiplication is not commutative. So in general, it is not commutative law. So in general, it is not true that AB is equals to B. A simple example of this can be just from the intuition, or what you can say. Let's say A is a matrix of uh, M cross N, and B is another matrix of, let's say, N cross P. Then if I multiply these two matrices A, B, the size will be like M cross P, right? And if I multiply B with A, the size will be, sorry, I made a mistake here. N cross M, then AB will be what? This is M cross M, but BA, this is N cross M. So if M is not equal to N, this is not actually true, right? So since the size of these two matrices is not equal, that means they are not actually equal. They are not actually equal matrices. So the example of matrix can be like 0 M cross N. Do you know what this matrix is? 0 M cross N. All the entries are 0. So it is, the size is M cross N, right? The number of row is M and the number of column is N. And like this, we consider another matrix. This is called I, or identity matrix of M cross N. So what is this matrix? Diagonally all the elements are. So this is like 1, 0, 0, 0, 1, 0, 0, 0, 1.
It's I M cross M.
Sorry. So I'm considering, yeah. So I'm considering just the identity matrix of N. So it is actually the number of row and the number of column is actually same. So it is a square matrix, and that's why it's the identity matrix. Right? And one thing that needs to be last, I want to say in here is, if A is an M cross N matrix, then IM A is equals to A, and it is also true that AIN is equals to A. So since it is an identity matrix, that means if I multiply it with another matrix, and if the multiplication actually makes sense, then that is equal to the original matrix. Right? So IM times A is actually A, and here the multiplication makes sense because the number of columns in the identity matrix is M, and the number of rows in the matrix A is actually what? M, right? So that's why this is equal to A, and similarly we can show that AIN equals to A. So finally, let us define another thing. So let A be a square N cross N matrix if there is a matrix B such that AB is equals to IN and BA is also equals to IN, then the matrix B is called the inverse of the matrix A and denoted by A inverse. So the previous line can be written as A inverse is equals to In, which is also equals to A inverse A. And if a matrix A is has an inverse, it is said to be an invertible matrix. So if the matrix A has an inverse, then we say A is an invertible matrix. So there is a very interesting proof here I'm going to do, and that is the uniqueness of inverse matrix. So do you think, is it possible that a matrix can have two different inverse? So let's prove it in a detailed way. So let B and B prime B so B and B prime inverse matrix of the matrix A. So what I can do is I can write B, and B is equals to B with the identity matrix, right? And since this is an identity matrix, so this has to be is equals to what? A times B prime. Yes. Right? So it follows from the previous equation here.
What are
Yeah.
you putting here?
So the uniqueness of the inverse matrix. Uniqueness of the inverse matrix. Okay. So by using the associative law, what I can do is I can write B A with B inverse, right? So here I used the associative law, this. So this is from this, I'm going this by using the associative law. And since B is also an inverse of the matrix A, that means this is equals to identity times B prime, and this is equals to B prime. Because we already showed that identity times any matrix is equals to that matrix, right? So that means there is only one inverse for a matrix, and So the uniqueness of this matrix inverse is proved from here. So from this we can actually write, let us consider the proposition. And the proposition is, let A B be n cross n matrices. So it is the first proposition in this course. Matrices if both are invertible so is there product and given by this is the first proposition. Okay, so this is proposition. Let's say in here this is 1.1. So this is the first proposition. So and this is equals to AB inverse equals to B inverse A inverse. And in a more general way, what we can write is if A1, A2, Am are invertible matrices, then so is the product. So is the product A1, A2, Am and its inverse is A1, A2, Am inverse equals to Am inverse, A2 inverse, A1 inverse. Okay, so we're going to prove this proposition. So first let us consider the first part of the proposition. This is AB inverse equal to B inverse times A inverse. And yeah, so yeah, if you take the multiplication and then you take the inverse, then it is actually in the opposite order, the inverse of B times the inverse of A. So the first part of the proof is simple. So what we can do is we can check if B inverse A inverse is actually the inverse of the matrix A times B. So what we can do is, like, we know already that if a matrix, let's say A, and the inverse of this matrix A is B, then we know that AB is equals to identity, and it is also true that BA is also equal to the identity, right? We are going to use this formula actually to prove the first part of this proposition, and this is actually, so if I multiply AB with B prime A prime, then this is equal to, so
In inverse.
I mean
Time inverse.
inverse. This is inverse A inverse, then I can use the associative law again, and this is equal to A with B inverse times A inverse, right? So far so good. Then the B inverse is the inverse of the matrix B, right? Yeah. So A and B is an invertible matrix, and A inverse is the inverse of the matrix A, and B inverse is the inverse of the matrix B. So, and now if I use the associative law here, so what I can write is A times the matrix B with B inverse multiplied by A inverse. So this follows that A with the identity matrix, so B inverse is the identity matrix, times A inverse, and this is equal to A with A inverse, and this is also equal to I. So, and now we have to check the later part, sorry, the opposite way. So for that, I'm going to multiply B inverse A inverse with AB, and this is equals to, again I can use the associative law here, right? And this is equal to what? B inverse with A inverse times A multiplied by B. So A inverse A is equals to the identity matrix. So this is equal to B inverse I times B, and this is equal to B inverse B, which is equals to the identity matrix. So from here we can conclude that the first part of the proposition is actually true, right? So the first part of the proposition is, if I take the multiplication of the matrices A and B, and then I take the inverse of this multiplication, this is equals to B inverse times the matrix A inverse. And for the second part of the proof, we are going to use the induction method. Okay. So for the second part, so if I let M is equals to just 1, then this is just what? This is just the only one matrix, and so if M equals to 1, then the proof is trivial. So this is A inverse is equals to A inverse, right? And now I'm going to take the assumption that the proposition, the second part of the proposition is true for M equals to some number K. And from this assertion, what I'm going to prove that it is possible the assertion, the second part of the proposition is also true for M equals to K plus 1. And if I can show that, the by induction method, I can say the proposition is true, right? So let us take the assumption that for M equals to K, the proposition is true. That means A1, A2, AM inverse is equals to, sorry, so AK, this is equal to AK inverse A2 inverse and A1 inverse. Now let us consider m equals to k plus 1. So m equals to k plus 1, if I take, then A1, A2, AK times A k plus 1 inverse. So here I also, okay, so here I also want to define something like P is equals to A1, A2, AK. The first K matrix, the multiplication of the first K matrix, then this is equals to P A K plus 1 inverse, right? Okay, so this is the definition, and from this, so from the first part of this proposition, P A K plus 1 inverse is equals to, so A K plus 1 inverse P inverse, right? So it is from the first part of the proposition. So, and we already know that P inverse is actually what? The inverse of the multiplication of all the first K element of the matrix, right? So this is equals to A K plus 1 inverse A K inverse A2 inverse A1 inverse. And from this, I can conclude using the induction method that the proposition is proved, right? Okay. Finally, for the matrix multiplication, I want to introduce you with the block multiplication. So block multiplication. So to define a block multiplication, let us consider. So we can actually decompose matrix into some different types of blocks. Okay. So for that, let us consider the matrix M and the matrix M prime. So the dimension of M matrix with size M cross N and N cross P respectively. Now let us consider a number R be an integer that is less than n. So we can decompose the matrix M and M prime like M B and M prime A prime B prime. So where can you tell me what is the number of column in the matrix A here? So I decompose this matrix in such a way that the number of columns in the matrix A is actually what? The number of column in A is R. So why I am taking this? So that the matrix multiplication makes sense. Right? So then the multiplication of these two matrices M and M prime is equals to A prime plus B prime. So if you decompose a matrix, then the multiplication is going to be a little bit easier to handle. Okay. A simple example is like 1, 0, 5 and 0, 1, 7 and
Excuse me.
yeah.
You defined M and N, but what about A prime and B prime?
So I say the number of columns in
A
the
prime is
in A is R. So what are the number of columns in A? I mean the array row in A prime.
R.
This will be R, and since R is less than N, so N minus R is the number of columns in B, right?
And vice rows.
You can, yeah. So, and another matrix, let's consider 2, 3, 4, 8, 0, and 0. So 5 and 7, 2, 3, 4, 8, 0, 0. So as you can see, the number of columns in the first matrix is what? It is 3. So I have to take a integer that is less than 3. So I can take it as like 2. So if I take it 2, then I can decompose the first matrix as in this way, and the second matrix in this way. So then the matrix multiplication will be 1, 0, 0, 1. This is the first matrix A times the A prime is here 2, 3, 4, 8 plus 5, 7 with 0, 0. Right? So now if I multiply these two, then this is 1, 2, 3, 0, 4, 8 plus, what is the matrix multiplication of the column vector? 5, 7 with 0, 0, that row vector. Yeah. So this is actually 0, 0, 0, 0. But the size is 2 cross 2, right? Because the row number of the first matrix is 2 and the column number of the second matrix is also 2. So that means this is equal to 2, 3, 4, and 8. So, but it is also possible to decompose a matrix not just in this fashion, I can do this for other, like I can decompose it into several parts. For that, let us consider let r plus s is equals to the number n and k plus l is equals to m. So r plus s, so I define the matrix M and M prime is of size m cross n and n cross p. And I'm taking the integer r and s, and the summation of this r and s is equals to n, and k plus l is equals to m. So do I have time? Yeah. So I can decompose the first matrix M is equals to 4 blocks by A, B, C, D, where so the column here A, the number of columns in the matrix A is what? Here this is R, and the number of columns in the matrix B is S. So that means R plus S is equals to N, and the number of row in the matrix A and B is also here it is K, and the number of row in the matrix C and D is L. Then this is K and this is L. So, and M prime is equals to A prime, B prime, C prime, D prime, and here the number of rows in the matrix A prime and B prime, this will be what? So we took R plus S equals to N, and the size of the matrix M prime is what? This is N cross P. So number of rows in A prime and B prime has to be equal R. This is R and this is S, right? So what is the matrix multiplication of M and M prime then? So M and M prime is equals to, I can multiply A with A prime, right? Because number of columns in A is R, and also the number of rows in A prime is R. So the multiplication of A and A prime makes sense. So the multiplication is A with A prime plus B with C prime, then A with B prime plus B with D prime, and C with A prime plus D with C prime, and C with B prime plus D with D prime. This is the matrix multiplication of this matrix.
Means M prime.
Yeah.
So the right side is you wrote TS, right? So
No, this is not. Sorry. This is actually RS,
RS.
because the size of the matrix M prime is N cross P, and it took R plus S equal to A.
That's the row, right?
Yeah.
RS.
R plus S equals to N.
What?
The column
The column here is, I didn't define it in a way because here the p is a different number, right? So m prime is n plus p, but okay, so okay, so right. I mean, there is no restriction. If you decompose the matrix M and M prime by this fashion, by just setting R plus S equal to N, it will match. I mean, the multiplication will be make sense, right?
You only have to like maintain the row for the like it
Yeah.
has to be R-based, but column can be
Different. So let me give you an example. I think that will help you. So the first matrix is here 1, 0, 5, and 0, 1, 7. And the second matrix is 2, 3, 1, 1, 4, 1, 0, 0, 0, 1, 1, 0. So now what I can do is, so there are 3 columns here in the first matrix, right?
Yeah.
So for R, let's set R equals to 2 and S equals to 1. Then the first matrix is decomposed like in this way. So I'm taking R equals to 2 and S equals to 1 here. Okay. So 2 plus 1 is equals to 3, and the first matrix is actually what? 3 column matrix. And for the second one, it is actually what? This is the number of row here will be 2, and so R for R equals to 2 and S equals to 1, this will be like this. Right? So the 2 plus 1, this is equal to 3, and this is the number of row in the second matrix. Right? So you see, I don't have to consider the number of columns in the second matrix when I'm decomposing matrix.
you can also decompose it into
Yeah, of course.
Is it because we have two columns and we are decomposing into one and one, that is why it's not happening? But if we decompose it into one rows and two rows and one, two and one, then
No, if you want to decompose it like,
let's take another row.
yeah, sure. So this is 1, 0, 5, and this is 0, 1, 7, and let's erase this.
No, I'm saying if we take another row in the first matrix.
Okay. So that is what I'm trying to do. So since this is a 3 column matrix, so I can take it like R equals to 1 and S equals to 2. Okay. So then what is the decomposition for this here?
No. I was saying that there are two rows in the matrix one.
Yeah.
But if we take three rows,
Yeah.
that is saying adding another row.
Yeah.
Okay.
First matrix.
Then I have to define like, okay. So let's say this is 2, 4, and 6. This is what you are saying. So let me see. This is So R equals to 2 and S equals to 1. So this is okay. So in that case, R equals to 2. If I decompose it like this, I have to make sense the multiplication here. 2 and so I still can decompose it in this way. Sorry. Two, 4, 1, 0. This can take this.
We need to wrap it up by 4:30.
Okay, sir. So there is 2
Yeah,
minutes.
2 more minutes.
Okay. So let me think about it, and
Sure.
I'm going to come back to
Do you
you.
have some study materials?
Yeah. For the study materials, we are going to follow these 3 books. Book 1, Algebra, by Mitchell Artin. Book 2, Algebra, by Kenneth Hoffman and Kunj. Linear algebra. Done right by Extra. We're going to follow these 3 books for this. Yeah?
Yeah, that pictures.
Yeah, sure. Okay. Sure. Thank you very much. And so we're going to meet in the next Thursday.